Hi everyone, this is Lesson 4, Video 1, Specific Heat Capacity. There will be 2 videos for Lesson 4. By the end of Lesson 4, it is hoped that you will be able to define specific heat capacity as the heat required to raise 1 kilogram of substance by 1 Kelvin without changing state. It is hoped that you will be able to derive specific heat capacity of a material from a temperature versus heat graph. It is hoped that you'll be able to recognize that every pure substance will have a unique specific heat capacity. It is hoped that you'll be able to conduct a calorimetry experiment to determine the specific heat capacity of a metal, and it is also hoped that you will be able to solve specific heat capacity calculations using the equation Q equals mc delta T. Let's begin with the definition of specific heat capacity using language. Specific heat capacity is the energy required to increase the temperature of 1 kilogram of a substance by 1 Kelvin. In the image you see here, we see a mass of water being heated by a Bunsen burner. Of course, the water is going to increase in temperature, but how much heat must the Bunsen burner supply to raise 1 kilogram of water by 1 Kelvin? That is specific heat capacity. In this slide, we see another version of the definition of specific heat capacity. This is a mathematical version. C equals Q over m delta T, where C is the specific heat capacity in joules per kilogram per Kelvin. Capital Q is equal to the heat received or supplied by the material in joules. M is the mass of the material in kilograms. And delta T is the change in temperature of the material. Take special note, delta T is T2 subtract T1. That means T new subtract T old. Sometimes delta T will be positive if the material is gaining temperature. Sometimes delta T will be negative if the material is losing temperature. Rearranging the equation, our definition for specific heat capacity gives us this incredibly useful equation, Q equals mc delta T. This tells us that Q, the heat associated with the change in temperature for the material, is proportional to the mass of the material and is proportional to the change in temperature of the material. And it's also proportional to the specific heat capacity of the material. Q, capital Q, can be positive or negative. It will be positive if our material is gaining temperature, and it will be negative if our material is losing temperature. Let's walk through a simple example. How much energy does it take to increase the temperature of 0.5 kilograms of copper from 20 degrees Celsius to 40 degrees Celsius? This question requires us to perform a simple calculation. And you have done simple calculations before in your Year 10 studies, and perhaps in your Year 9 and Year 8 studies as well. But for now, we're going to do this simple calculation. And while we're doing this simple calculation, we're also at the same time going to be thinking about best practice calculation solving strategies. So this question, as simple as it is going to illustrate specific heat capacity for us, and at the same time is going to illustrate good practices for answering calculation questions. With that in mind, when we do a calculation, one of the first things that we do is we interrogate the question. Now, what does this mean? It means we go through with our highlighter or our red pen and we underline the key parts of the question that we're going to use in the calculation. Let's do that now. So, the key parts of this question are going to be the mass of the copper, the fact that it is copper, and the temperature range that the copper is going to move through. Having interrogated the question, we now go to the trouble of listing our givens. The usual practice for listing your givens is to make a list of what you've gotten from the question in the top left-hand side of your space. When we interrogated the question, one of the first things we noted was that it was using copper. So we go to our textbook or we look it up in a formula and data sheet, and we see that copper has a specific heat capacity of 390 joules per kilogram per Kelvin. You're not expected to memorize the specific heat capacity of different materials. If you need a specific heat capacity in a question, it will always be given. Or, alternatively, it might be that the question is asking you to figure out what the specific heat capacity of the material is, in which case it won't be given, but everything else will. Continuing with our list of givens, we see that capital Q, heat, is the actual focus of this question. This is what we're trying to figure out. We note from the question that the mass of our copper is 0.5 kilograms and that the delta T is going to be positive 20 Kelvin. We were given 20 degrees Celsius as the starting temperature. We were given the final temperature as 40 degrees Celsius. That is the increase of 20 degrees Celsius. When it comes to delta T, a delta T of 20 degrees Celsius is the same as a delta T of 20 Kelvin. The next step in answering the calculation is to declare the equation that we're going to use. In this case, it is Q equals mc delta T. Following this, we input the numbers that we've been given, and we do this underneath the declaration of the equation. In physics, we like to put our calculations running down the page, and as a general rule, we like to try and make the equal signs line up with each other going down the page. This is good presentation, and it makes it easy for the examiner to follow your reasoning. Finally, we write out our answer and we don't forget to put in the units, 3,900 joules. This particular question is an example of something I like to call a plug and play question. We're given all the data we needed. We had to look up the specific heat capacity of copper, and then we just plug it all into the equation. We didn't even have to rearrange the equation. This calculation is a simple example of specific heat capacity calculations. So, we've answered our first calculation for specific heat capacity, and we came up with an answer of 3,900 joules. We had a mass of 0.5 kilograms. We were working with copper, and the delta T was from 20 degrees to 40 degrees Celsius. What would be the answer if, instead of 0.5 kilograms of copper, we had 1 kilogram of copper? Well, if we did the calculation again, we would get 7,800 joules, double the mass, double the heat. What would be the answer if we kept the mass the same, but we doubled the temperature range? Well, if we do our calculation, it comes up again to be 7,800 joules, double the delta T, double the heat, everything else stays the same. So, what would the answer be if we doubled the mass but we halved the delta T? Well, doubling the mass would double the heat, halving the delta T would halve the heat, and we come right back to 3,900 joules. We could do this all day. We could come up with different versions of the same question all day. I'll leave you to do that in your own time. Here's a new question. How much energy is released when 800 ml of water is allowed to cool from 80 degrees Celsius to 30 degrees Celsius? This is a new question because we've got a couple of new things happening in this question. First of all, we're not dealing with copper, we're dealing with water, so we'll have to look up the specific heat capacity of water. Secondly, our delta T is actually negative this time because the new temperature, the final temperature, is less than the initial temperature. And finally, the other new thing that's appearing in this question is that we're not given the mass of the substance, we're given the volume of the substance, 800 milliliters. Fortunately for us, in physics, we often use volume and mass for water as interchangeable because of a convenient little property of water in that 1 liter of water is 1 kilogram of mass. So, for water, 800 milliliters, or 0.8 liters, is the same as 0.8 kilograms. Okay, so having identified the differences in this new, slightly more challenging question, let's now go through and interrogate the question by highlighting the important parts of the question. We're asked how much energy is released. That word, released, is significant, and we'll come back to that word at the end of this question. We are given a volume of water, but as we mentioned, we now know that for water, 800 ml of water is 0.8 kilograms because of that convenient physical property of water where 1 litre is 1 kilogram. We're told that it's water and not copper. So we go to our formula and data sheet and we look up water and we see that water has a specific heat capacity of 4,180 joules per kilogram per Kelvin. And we see that our delta T is going to be negative. So we interrogate the question, we highlight, we underline these important parts of the question, and then we list our givens. Here are the givens that we've taken from the question. Take a special note here. Delta T is negative 50 Kelvin. That's going to be very important in this question. Having listed the givens, we now declare the equation we want to use. You must always declare the equation you want to use. It may seem obvious at the moment, but as you move through your physics journey, you'll see that there are many equations that can be used to solve different problems, and it's important that you tell the examiner always which equation and which strategy you're using. The rest of the question is easy to resolve because it's now a plug and play question. Again, we just plug in the numbers, remembering that delta T is T2 subtract T1, so that gives us a negative value of negative 50 Kelvin, and that leads us to an answer of Q is equal to negative 167,200 joules. The negative in our answer indicates to us that Q is a heat loss. Now, if you look back up to the question, it does ask us how much energy is released. Now, we might say that Q is equal to negative 167,200 joules, but that is not an answer to the question that has been asked. In physics, you must always answer the question that has been asked. So while Q is a negative value, we need to actually answer the question asked. And so we say at the end of the question that Q, the heat released, is 167,200 joules released. So Q itself is a negative value, but the energy released out there into the universe is a positive value. Having now played around with a specific heat capacity equation and having done a couple of calculations, let's now look at the fact that specific heat capacity is a unique property for all materials. This can be illustrated in the graph below. In this graph, we see 4 different materials: copper, aluminium, iron, and water. Each of these materials is 1 kilogram, and this graph shows that the temperature of each of these 4 different materials is changing as we add heat to each of them. So this graph shows the results of an experiment that was done at some point in the past in some lab somewhere in the world. What's significant for us, though, is that we can see that each material has the same mass, each material has the same heat added to it, they all have the same starting temperature, and yet their final temperatures are not equal at all. This indicates to us that the specific heat capacities for each of these materials is different. And the result is that each material has a very different temperature after 10,000 joules of heat is added to them. Copper comes in at 46 degrees Celsius, iron comes in at 43 degrees Celsius, aluminium comes in at 31 degrees Celsius, and water hardly rises at all as it comes in at 23 degrees Celsius. We see that each material behaves in its own way and changes temperature in its own way due to the fact that each material has its own unique specific heat capacity. To illustrate this idea further, this table shows the unique specific heat capacities of a number of different materials. I've taken this table from chapter 1.2 of your Pearson text. It's interesting to note that liquid water has an enormous specific heat capacity when compared to many other materials we see. The metals in this table, iron, copper, brass, lead, and mercury, are all quite low when compared to liquid water. The unique nature of specific heat capacity also lends itself to the idea that when we have a mystery metal or a mystery material, if you're able to determine the specific heat capacity of the material, then that actually reveals to you what the material is. And in week 3, that's exactly what we're going to do. We're going to try and measure the specific heat capacity of a mystery metal in week 3, but we'll talk more about that in the next video. Right, So that brings us to the end of Lesson 4, Video 1. So what do we do now? Take a moment to jot down the ideas from this video into your physics notebook. Try to do them from memory. Don't just go back and copy them word for word. Go read and take notes on Chapter 1.2, Specific Heat Capacity, from your Pearson Physics text. And then start doing Chapter 1.2, Specific Heat Capacity questions from your Pearson Physics text. And also, I want you to start looking at the Exploring Physics Problem Set 3. Get as far as you can in those. And when you're ready, have a look at Lesson 4, Video 2. I hope this was useful.